To finish out Chapter 6, we're going to be looking at sampling distributions and the central limit theorem. Your objectives here are going to be to describe what a sampling distribution is and identify their behavior, describe the requirements for applying the central limit theorem, and apply the central limit theorem to find probabilities associated with sample means. Here we have an example. Suppose heights of adult men are approximately normally distributed with a mean of 68.9 inches and a standard deviation of 2.8 inches. How likely is it to see a randomly selected man who is more than 72 inches tall? So we have our mean and our standard deviation, and we are looking for who is more than 72 inches tall. The problem told us that we are supposing that the heights of men are approximately normally distributed, so we are going to be able to use this norm.dist formula. You just had to be careful because when you sketch your curve, we are looking for greater than, so that's the above part. So we have to use 1 minus norm.dist 72, comma, our mean of 68.9 and our standard deviation of 2.8. 1 is the same as true. So if you see a 1 in any of these notes, just know that that's the same as true. And we get approximately 0.1341 as our answer. And here you can see this problem completely worked out. So what we're saying is seeing a random adult man who is taller than 6 feet is not terribly surprising. There's about a 13% chance. So here we're saying, well, suppose the heights of men are approximately normally distributed with a mean of 68.9 inches and a standard deviation of 2.8 inches. How likely is it to see a group of 50 randomly selected men where the average height in the entire group is more than 72 inches tall? Is this more likely, less likely, or the same chance as seeing a random male who is more than 72 inches tall? And remember, that one was 0.13. So notice the problem has changed. We have now went from looking at just a random male to a group of men. So to figure out how likely it is to see a group of 50 randomly selected men where the average height in the entire group is more than 72 inches tall is actually a lot less likely. Okay, so here's the probability. So the probability that the average height is greater than 72 is very, very, very small, and you can see that there in your answer. So we have some notation reminders we need to just go over. Of course, mu is our population mean, x bar is the sample mean, x is a single observation value, sigma is a population standard deviation, s is the sample standard deviation, and we have new probability. So now we have the probability of x is greater than a number means the probability that a single observation is higher than some number. If you see the probability of x bar greater than a number, it is the population that the mean of a sample is higher than this number. And so you'll need to be careful on how these problems are asked. When we talk about a random variable being bell-shaped or skewed, we're discussing the distribution of that variable. The heights of men are normally distributed. The number of puppies in a litter is skewed right. The wait times in line at a bank is uniform. Those are all different types of distributions. Statistics like x bar, s, and others also have distributions. The distribution of a statistic is called a sampling distribution. In this class, we will be primarily considering the distribution of sample means, or x bars. A sampling distribution is formed when we repeatedly take samples of the same size. So we're taking samples over and over of the same n. If we understand how a sampling distribution behaves, looking at the shape, the mean, the standard deviation, then we can use that information to do inference. For example, the height of adult men. So here are our conditions so that we can use the central limit theorem. Either the original population is normally distributed, so that would just be in the problem and state that we are assuming that the population is normally distributed, or the sample size is greater than 30. So in either case, either one can be true, or both could be true for us to be able to use the central limit theorem. Some properties: if x bar is normally distributed, then the mean of all the x bars is the same as the mean of the population. So think of this as the mean of the sample means, and we will see things like mu sub x bar. The standard deviation of all x bars is sigma over the square root of n. This is also called the standard error. So you need to make sure that you're connecting standard deviation of the sample means and standard error. And to find that, it is sigma over the square root of n. So you're going to do standard deviation divided by the square root of the sample size. So just so you can see what we're saying here is if we have a population that is distributed and it's not a normal sample, then as our sample number increases, or we take it over and over and over, then we start looking like a normal distribution. So if either condition is met, we know that the sample means tend to be normally distributed. The mean of the sample means is equal to the mean of the population. So mu sub x bar is equal to mu. The standard deviation of sample means, so sigma sub x bar, is equal to sigma divided by the square root of n, also called the standard error. So again, this new notation, mu sub x bar is the mean of the sampling distribution of means, or just the mean of the x bars. And sigma sub x bar is the standard deviation of the sample means, also known as the standard error of the mean. Our conditions would be so either one of them or both of them must be met. The original population must be normally distributed, no matter what n is, as long as the problem says it's normally distributed. You can use the central limit theorem. Or the sample size must be higher than 30. So that means no matter what the distribution of the original population, as long as your n is greater than 30, you can use the central limit theorem. So looking back at that height of men, we have that suppose heights of adult men are approximately normally distributed with a mean of 68.9 inches and a standard deviation of 2.8 inches. How likely is it to see a group of 50 randomly selected men where the average height in the entire group is more than 72 inches tall? So are the central limit theorem conditions met? So is the population normally a normal distribution and the sample size greater than 30? So here you can see, yes, it tells us the heights of men are approximately normally distributed. So one of the conditions is met already. In our next one, we can see that, yes, the sample size is greater than 30 because we're looking at a group of 50 men. So in this case, we can use the central limit theorem because both of them hold true. So how likely is it to see a group of 50 randomly selected men where the average height in the entire group is more than 72 inches tall? So what do we know about x bar? So from our central limit theorem, we know it's normally distributed, so we can use norm.dist. And remember that mu sub x bar is equal to mu, so in this case, it's 68.9 inches. Sigma sub x bar is equal to the standard deviation divided by the square root of n. Our standard deviation is 2.8 and our n is 50. So you're going to do 2.8 divided by the square root of 50. So how likely is it? We can go straight to our Excel, and we know that our probability is going to be x bar greater than 72 because, again, we're talking about a group of 50 randomly selected men. So because we've got a group of 50 randomly selected men, we do have this x bar. And in Excel, so we're, again, sketch, you're shading above. Because we're shading above, we need to do 1 minus norm.dist. And then you're going to see here where I'm using the same norm.dist, I'm just using some new information in one place. So our x is still staying the same. So in this case, it's an x bar. we have our mu sub x bar, which is equal to mu. And then here we have sigma sub x bar. Now remember, this is the standard deviation, so you should have sigma divided by the square root of n. And that's what you can see here in 2.8 divided by SQRT parentheses 50. And then we'll finish with that true statement. And when you put this into Excel, that's how you're getting that very, very small probability that we saw toward the beginning of this lesson. So let's look here at the elevator and car rental building at San Francisco International Airport has a sign stating that the maximum capacity is 4,000 pounds or 27 passengers. When the elevator is full, this converts to a mean passenger weight of 148 pounds each. Let's assume a worst case scenario in which the elevator is filled with 27 adult males. Assume that adult males have weights that are normally distributed with a mean of 189 and a standard deviation of 39 pounds. We're going to look to see if we can find the probability that one randomly selected male has a weight of greater than 148 pounds, and then find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. We are looking first for the probability that a single male has a weight of greater than 148 pounds. So we are dealing with an individual X value from the normal population distribution, so you should have P parentheses X greater than 148. We are working with a normal distribution, so you're going to be looking at using that norm.dist. And you will be finding, again, we're looking for greater than. You can see that shaded green region, so we're going to need to do 1 minus your norm.dist of 48, 189, 39, comma, true. And that gives us 0.853435. So what this is saying is that we are having about an 85.3% chance that a single male weighs more than 148 pounds. And number 2, we're looking to find the probability of a group of males that has a weight of more than 148. And this is a group of 27. So the first thing we have to think about is, can we use the central limit theorem? So we can use the central limit theorem if the original population is normally distributed or n is greater than 30. So this sample size is not greater than 30, right? We're looking at 27 men, but the original population of the weights of males has a normal distribution, so we can use the central limit theorem. So since x bar is normally distributed, and so mu sub x bar equals mu, so our means are the same, so 189, and then of course your standard deviation of the averages is equal to the standard deviation divided by the square root of n. So we're going to do 39 over the square root of 27, and that gives me approximately 7.51. We will be using these new values in our Excel formula. So we are looking to find the probability that the group of men has a weight of greater than 148. So what we're going to do, again, we're looking for area to the right, so we have to make sure we do the complement rule. So we're going to do 1 minus norm.dist, 148, 189, your 39 divided by the square root of 27, and then comma 1 or true, and when you get that, you get 0.9999998. So what this is saying is that there is a 0.8534 probability that an individual male will weigh more than 148 pounds, and there is a 0.9999998 probability that 27 randomly selected males will have a mean weight of more than 148. So given that the safe capacity of an elevator is 4,000 pounds, it's almost certain that it would be overweight if it is filled with 27 randomly selected adult males. So if we make a certain assumption about a population and we see a sample that is significantly unlikely, meaning, for example, the sample mean that we observed has a very low probability, then we conclude that our original assumption is probably incorrect. So let's take a look at this body temperature example. A common belief or assumption is that the human body temperatures have a mean of 98.6 degrees Fahrenheit. Suppose we take the temperature of N of 106 random healthy adults and we see that the average is 98.2. Is this observation significantly unlikely given our assumptions? So for this problem, let's assume that our standard deviation is 0.62 Fahrenheit, and this is based on a study from the University of Maryland. So we have a mu of 98.6 and a standard deviation of 0.62. So what's the likelihood of seeing a sample of 106 random adults with a mean temperature of 98.2 or lower? So because our N is 106 and that is greater than 30, we can use the central limit theorem. So what we are looking for is the probability that X bar is less than 98.2. We'll use equal norm.dist 98.2, comma 98.6, comma, now this is where that central limit theorem is really coming into play, 0.62 divided by the square root of 106, comma, true. And when you put that into Excel, you should get approximately 0.00000000000015437. So if our assumption were really true, then it's astronomically unlikely that we would see a sample of 106 adults with an average temperature of 98.6. So therefore, our assumption must be incorrect, and it turns out that the true mean body temperature is closer to 98.2 than 98.6. So that normal distribution, we've done a lot of different normal distributions. So here's a little flow chart for you to help keep track with everything that we've done. The first thing, is the problem asking about an X, or is it asking about a sample mean, that X bar? So then you'll move from there, and if you're looking at a single value, you're going to come up here, and then you'll go across, right? So is it asking us to find a probability or an X value? If you're a probability, you use norm.dist. If you're an X value, that's when you use norm.inverse. Now, if it is asking about a sample mean, then that is where you will move down. And then, is the original population normally distributed? Well, if it is, you can use the central limit theorem. Just make sure you keep in mind that that standard deviation is going to have to be the standard deviation over the square root of n, and then you can use norm.dist. If the original population is not normally distributed, then you have to say, okay, well, is the sample size greater than 30? And if it is, you can use the central limit theorem. If it is not, then you cannot answer the question. So this finishes up Unit 2 material, and you can now work on lab manual pages 53 to 55, and of course your My Stat Lab homework section that is 6-3, 6-4 together. And then that My Stat Lab quiz. If you have any questions, please post them in the Teams channel Unit 2 questions.